Hey there, my name is André Pereira and I'm presenting our work on the effects of different interaction contexts when evaluating gaze models in HRI. This is joint work with Catharine Oertel, Leonor Fermoselle, Joe Mendelson, and Joakim Gustafson. If social interaction partners are mutually aware that they are attending to a common target, that phenomenon is generally described as joint attention, which is the focus of our work. This usually involves several phases. Mutual gaze is used to establish attention, then referential gaze is used to draw attention to an object of interest. The other party then typically responds and establishes joint attention. And finally, mutual gaze is established again to ensure a shared experience. In HRI, joint attention has shown that it can make cooperation with robots more efficient. For example, a robot in a factory assembly line should ideally perceive collaborators' attention and also provide cues that demonstrate its own attention and what it is going to do next. Social gaze behavior generation is also important for creating the illusion of human-like appearance and behavior, which is the focus of our work. We previously introduced a responsive joint attention system that perceives multimodal information from users and can communicate joint attention via controlling a robot's gaze. An initial evaluation of our system in a spatial reasoning task with adults showed it to improve users' perception of the robot's social presence. To investigate the repeatability of our prior findings, we conducted two further studies that employ the same gaze system with the same robot and the same task, but in two further contexts. We wanted to find out if results from a situated first-person perspective generalize to observers watching videos from a third-party perspective. And also, if we can generalize our initial findings from adults in the lab to children interacting with the robot in a school environment. To study our gaze model, we created a task where a robot can collaborate with participants.
You're doing great.
The participant's goal in the task is to visualize a 3D cube structure and reconstruct it in 2D.
Are you really sure?
Can you repeat the question?
Okay. I would probably remove this yellow piece.
A semi-autonomous wizard interface is used to control the robot's high-level behaviors.
Tell me the limitation again.
In this second round, we must use at least 3 squares in line, but not more.
Participants have to complete 3 rounds with increasing difficulty.
This arrangement does not really look correct.
So how does our gaze system work? It is composed of a 2-layer design, a proactive gaze layer that initiates joint attention, and a responsive gaze layer that responds to attention cues. It can simulate joint attention in any scenario where a robot interacts with a user in a certain environment while collaborating in a task. Each layer contains different modules, and starting in the proactive layer, a decision-making model, controlled by a human wizard, selects when the robot should perform a dialogue act. When dialogue acts are targeted at a user, the robot attempts to establish eye contact, and when dialogue acts are targeted at task objects, the robot attempts to initiate joint attention towards those objects. The idle gaze module controls the robot's gaze in moments of inactivity. Idle gaze shifts occur when the speech content associated with the dialogue act finishes, or the timer for any previous gaze shift ends. Idle gaze can target users, objects in the task, or looking at a random point in the environment, which makes it seem that the robot is distracted or averting its gaze. The responsive gaze layer uses real-time multimodal perception to minimize the robot's idle time and increase the usage of more meaningful responsive joint attention behavior. Our gaze tracking module enables the robot to look at approximate positions of the task that the users are looking at. And it can also look back at users if they shift their gaze towards the robot. This is essential to create a feeling of responsive joint attention, as when trying to establish joint attention, users tend to start and finish with mutual gaze. Object tracking detects when a user moves, places, or removes a puzzle piece from the board. Here, the robot often assumes that the piece is the current focus of attention and can, of course, gaze at that location. Our last responsive module is speech activity. When speech activity is detected and the robot is not engaged in a higher priority gaze command, the robot attempts to establish mutual gaze with the user to simulate listening behavior. For extended details on how the gaze system works, please consult the original IRIS paper and our GitHub project page. We evaluate our joint attention model in 2 different conditions. The control condition represents the typical HRI method of most robots and only uses the proactive gaze layer with decision-making and idle gaze, We carefully designed the idle module to exhibit believable gaze behavior with the goal of making a fair comparison with the full condition. The full condition is as the name says and uses the full model that we just described with both proactive and responsive layers. Our hypothesis is that adding this extra responsive layer will result in the robot being perceived as more socially present. By looking at our objective data and matching the gaze patterns of the users and the robot, we look into measures of gaze synchrony, and we also look into the subjective measure of social presence. Social presence is defined as the sense of being together with another. We are using the network mind's measure of social presence that is divided into 6 dimensions with 2 distinct directions. The bidirectional nature of this measure makes it a sound choice for evaluating the effects of each type of joint attention individually, initiating joint attention and responding to others' joint attention. In this paper, we look into the perception of the robot direction as we manipulated the presence of responsive joint attention behaviors. The first replication study we performed had the intention of testing whether third-party observers could perceive the full condition as more socially present. We created a crowdsourcing task where in one video the robot was running the full condition and in the other the control condition. The same actor was responding similarly to the robot in both videos, and both the actor and the robot displayed the exact same verbal behavior. Crowd workers viewed each video separately with a length of approximately 1 minute and 50 seconds and could rewatch the videos as many times as necessary to reply to a set of forced choice questions. This study suggested that external observers do perceive social presence differences between our conditions, as they consider the robot in the full condition as more aware of its interaction partner, more capable of understanding messages, and more emotionally involved with the user in the task. Now, we will compare our 2 real-time studies where participants interacted with the robot in real time. In the original study with adults, we observed positive significant differences in message understanding and in the total social presence measure. We expected that when replicating our study with children, they would be more engaged with the task and it would result in even clearer findings in support of our hypothesis. Although children rate the robot significantly higher in our social presence items, the study revealed no significant differences in the social presence measures between conditions. Despite not reporting differences between our gaze conditions, children, when compared to adults, found the robot to be more helpful, would be willing to cooperate more with the robot in the future, and liked and trust the robot to a greater extent. In both conditions, either because the task or the robot was more compelling for children, or because of their tendency to please the experimenters, most of the children's scores approached the upper bound of our Likert scales. This might have made it more difficult to find differences between our conditions. Regarding behavior synchrony, we can observe a significant difference when we compare the amount of joint attention in both groups. Overall, children exhibited a greater amount of joint attention. These differences can be explained by the fact that children looked much more at the board, which gave the robot more opportunities for establishing joint attention. And children looked more at the board because they exhibited more difficulties. This is confirmed by our direct question that asks participants how difficult they found the task, and in several of our objective measures that point to younger participants having more difficulties in completing the task. To conclude, the results from the 2 replication studies reported in this paper suggest that our main hypothesis was supported with external observers, but not with children. Our findings suggest that the HRI community should take into consideration the selection of an appropriate task and interaction context that provides significant opportunities to observe the robot's behaviors. While we initially thought that our task would be more engaging for children and thus more appropriate to evaluate our gaze model, it appears that external observers and participants that established increased levels of mutual gaze with the robot were more successful at detecting improvements in our manipulated behavior. Children had greater difficulty with the task, which reduced their attention to the robot, and in turn might have reduced their ability to perceive the robot's responsive joint attention behaviors. In addition to providing further evidence that supports our initial finding with adults, the results from the observer study afforded us with the confidence to perform additional real-time studies. Although external observer studies can often be more limiting due to participants not being situated in the interaction, they can have the advantage of being designed in a way that users are already visualizing the target robot with the target behaviors, which can provide very accurate preliminary evaluations. And this concludes my presentation, and thanks for your attention.